Hey there, Andy here. So in this episode, I want to talk about some of the properties of hydrocarbons. Of hydrocarbons, which is a common topic that will come up a lot on the MCAT OChem section. So there are three main properties that you need to be aware of for taking the test. The first one is trends in boiling point. Now, as you probably know, boiling point is the temperature at which a liquid goes into the gas phase. But for the OChem section, you need to be aware more of the trends in boiling points in hydrocarbons. So let's take an example. Let's say we have a small hydrocarbon, butane, versus a larger one, say octane. 3, 4, 5, 6, 7, 8. Both are straight chains, and we'll talk about branching in a second. But for the point of finding trends in boiling point, we want to look at straight chains. So obviously octane, butane, octane. Octane is obviously has more hydrocarbons bound together and a higher molecular weight. So higher, and this is a lower. Butane has a lower molecular weight. And so when things have a higher molecular weight, they have a higher boiling point. And when they have a lower molecular weight, they have a lower boiling point. Now, why do you think that's true? Well, because as you have more carbons bound together, you have more bonds, and it takes energy to break those bonds. So the boiling point reflects that energy that you need to break the bonds to change from a liquid to gas phase. So straight chained hydrocarbons with a higher molecular weight will have a higher boiling point. I mentioned branching earlier, and that's the next trend we need to be aware of. Branching. Branching is basically talking about substituents. So let's say we have this molecule uh, versus a molecule with two substituents. And remember, substituents are, basically side chains that come off of the main chain of hydrocarbons. 5, 6, 7, 1, 2, 3, 4, 5, 6. Okay, so let's put 2 there. So there are two substituents on this hydrocarbon, and more substituents. Let's write this down. Higher branching, which means more substituents, will result in a lower boiling point, whereas less branching results in a higher boiling point. Now, why is that? Well, as you have more branching, the bonds actually get in the way of each other, and it makes it easier to break them. And also in biological systems, when you have less branching, it's easier to stack. So, for example, if I drew more of these chains for the non-branching molecule, and you can tell, like, if I try to draw stacks of the branching, it's much harder and less dense. So when you have a more dense molecule, you need more energy, and that's reflected by the boiling point. So let's look at an example of that. We have, let's choose a random color. We have trimethyl pentane versus let's do 2-methylheptane. 1, 2, 3, 4, 5, 6, 7. Okay, so trimethylpentane versus 2-methylheptane. This trimethylpentane has more substituents. Right here has 3 substituents, whereas this one only has one. And so we expect the more branched molecule to have a lower boiling point, and in fact it does. It has a boiling point of 99 degrees Celsius, and the 2-methylheptane has a boiling point of about 119 degrees Celsius. So we can see less branching leads to a higher boiling point. Okay, the third property of hydrocarbons we want to talk about is called degrees, also known as, they refer to as units, of saturation. And what exactly does that mean? Well, when we're talking about hydrocarbons, usually carbons are bonded to hydrogens. And so saturation basically means, how many hydrogens are bonded to each carbon. So something is completely saturated. Complete saturation means that there are no, no double bonds or triple bonds. There are only single bonds. Only single bonds. And any degree of unsaturation can be a result of any double or single bonds, or excuse me, double or triple bonds. Triple. Or can be caused, unsaturation can be caused by ring structures. And there's a handy equation that you should memorize to talk about degrees of saturation. In OChem, there are very few equations that you need to know, but this is probably one of them. So the degrees of saturation is equal to 2n plus 2 minus x divided by 2, where n is equal to the number of carbons and x is equal to the number of hydrogens. So let's take an example. Let's say we have, let's go down a little. Let's say we have cyclohexane. So cyclohexane has 6 carbons, one at each vertice. 6 carbons. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So let's calculate that. I'm going to have 2n, which is going to be 6 carbons, plus 2, close parentheses, minus 12 hydrogens. Oh, it's the wrong shade of blue. 12 divided by 2. So 2 times 6 is 12, plus 2 is 14, minus 12 is 2, divided by 2 is 1. So there is 1 degree of saturation with cyclohexane. Excuse me. Let's look at something else. Let's look at a benzene ring. So it's basically a cyclohexane with 3 double bonds. So we're going to have the same amount of carbons, 6 carbons. But now we're going to change the amount of hydrogens. So there's only going to be one, let's use a different color. There's only going to be 1 hydrogen for each carbon. So we have only 6 hydrogens. And now let's look back at this formula. So it's going to be 2 times 6 carbons plus 2 minus 6 hydrogens. Oh, minus 6 hydrogens divided by 2. So 2 times 6 is 12, plus 2 is 14, minus 6 is 8, divided by 2 is 4. Let's make a better 4. 4. So let's look at this. As we became more unsaturated, we added double bonds. Remember, we went from cyclohexane to these double bonds in the benzene ring. As we became more unsaturated, which means we lost hydrogens, we increased our degrees of saturation. Okay, so you don't really need to worry too much about the wording. Usually, if you get a question like this on the MCAT, it's more about figuring out the math than knowing, the different definitions of unsaturation and complete saturation. So just remember that saturation is talking about the number of hydrogens bonded to your carbons.